Okay, thank you. So I'm going to give you an update on the development of coupled NWP forecasting at the Met Office. I've done this work, well, I've presented the slides with the help of Tim Graham, Michael Blinker, and Chris Harris, but then a lot of other people have also contributed towards developing the coupled NWP model at the Met Office. I want to acknowledge them too. Okay, so the talk will be in 3 sections. I'll start off with looking at a coupled NWP model versus an atmosphere-only NWP model. So currently we're running atmosphere-only NWP in our operational forecasting system. So I want to make sure that the coupled NWP model is at least as good as, if not better than, the operational model. Then I'm going to talk about operational implementation, other sort of additional hurdles to make it operational. Then I'm going to talk about some future changes that we're going to put in after it becomes operational. Okay, so the Met Office plans to move to coupled NWP for its operational weather forecasts in the next year or 2. So the results presented here are for the PS41 coupled NWP model, which is the PS41 refers to the science in the model. So this consists of the components shown on the right. The atmosphere is based on our unified model, and the land surface uses the JOULES model, Joint UK Land Environment Simulator. The UM and JOULES compiled into the same executable and communicate at the subroutine level. For the ocean, we use the NEMO ocean model at NEMO 3.6, and for the sea ice, we use the SICE sea ice model using SICE 5.1.2. And again, these are compiled into the same executable and communicate at the subroutine level. So the NEMO and SICE models use the ORCA grid, the tripolar grid. UM and JOULES use a latitude-longitude grid. So they communicate by the OASIS-3 MCT coupler every hour. I should have really drawn the OASIS arrows in between the UM and NEMO, because it's the UM and NEMO parts of the code that have the sort of OASIS get and put commands, and then they pass the information onwards to the JOULES and SICE subcomponents after that. So the physics options. So the middle column is the operational model, and the right-hand column is the coupled NWP model. So the physics options are the same between the 2 models that I'm comparing. The atmospheric resolution is N1280, which is about 10 kilometers grid spacing in mid-latitudes in the atmosphere. The number of vertical levels in the atmosphere is 70 levels. The sea surface temperatures and sea ice from the operational uncoupled model are provided by Austia, which is a sea surface temperature and sea ice analysis software, and they are then kept constant throughout the run. For the coupled NWP model, the ocean and sea ice initial conditions are provided by a NEMO SICE data assimilation system called FOAM, and then they then evolve throughout the forecast. The land sea mask is also different between the 2 systems. So the operational atmosphere-only model uses IGBP to derive its land sea mask, which does include some large lakes and sea points, whereas the coupled NWP model uses the NEMO land sea mask, then regridded to the atmosphere grid. The horizontal resolution of the coupled NWP for the ocean is ORCA quarter, so about 25 kilometers, 75 vertical levels in the ocean, and again, coupling every hour. So this is some sort of top-level verification statistics. So this is based on root mean square errors, comparing against our operational UM analysis. So in the plot on the right, the x-axis is forecast lead time into the forecast, and then all the symbols on the y-axis are different fields in different regions. So we've got pressure at mean sea level, the winds at various heights, temperatures at various heights, and the geopotential heights at various heights in the different regions. And the green up arrows are where the root mean square errors have reduced and the model has improved. And the blue down arrows are where the root mean square errors have increased, so the model has degraded. So you can see that the coupled NWP model has improved in virtually all fields, apart from 2-meter temperatures in the different regions. And part of the reason for that is that the uncoupled model is sort of unfairly at an advantage, because both the UM analysis and the uncoupled model both use Austia sea surface temperatures and sea ice. So that's giving an unfair advantage for sort of closely related fields like 2 meter temperatures that are very closely related to sea surface temperatures. And this is fixed by comparing to a weakly coupled data analysis system, which I'll come on to later. I should also say before I move on that all the results presented, all the plots in the next few slides are already published by Berlinger et al. In Weather and Forecasting Journal. Okay, so one of the things we wanted to check was to make sure that the sea surface temperature forecast for the coupled NWP was better than persistence, which is what the atmosphere only model does. So this is mean absolute errors on the top and variance of difference between forecast and observations on the bottom, for day 2 on the left and day 7 on the right. Blue is basically where the biases have reduced and the model has improved, and red is where the biases have worse. So you can see that generally the model's improved, especially in the subtropics and the northern higher latitudes. So the sea surface temperatures outperform persistence, but unfortunately there's a thin strip in the Southern Ocean where the model sea surface temperatures for persistence is actually better. And this is an area of active investigation in the Met Office. So we're trying to fix our Southern Ocean sea surface temperature biases. Some of those plots in the verification plots earlier on were for geopotential height and 250 hectopascal winds, and so these plots show the regions where we're seeing the most of those improvements. So if you just focus on the sort of plots on the right, that's the variance of difference plots. The blue symbols show where the models has improved the most, and the improvements are mostly in the equatorial regions. And this is where there's deep convection, and having a feedback with the sea surface temperatures in the couple model provides an advantage to the couple model. So you have deep convection, and then that sort of suppresses the sea surface temperatures underneath it, and that sort of negative feedback can improve the large scale circulation, improving those geopotential heights and 250 hectopascal winds. We've also got a tropical cyclone tracking algorithm within the model. So during the forecast, we track tropical cyclones, and we designate them either as similar, as in the couple model and the uncoupled model are too close together, or we say either the coupled NWP model is superior or the uncoupled model is superior. And then if you average over all the tropical cyclones throughout all the forecast for over a year and a quarter, then you get this plot here, and you can see that after about 84 hours lead time, the coupled NWP model starts to forecast the tracks of tropical cyclones more accurately. So by 132 hours into the forecast, the coupled NWP model predicts better tracks 40% of the time, whereas the uncoupled model only predicts better tracks about 20% of the time. So that's quite an improvement to tropical cyclone forecasting. And part of that is probably because of the large scale flow is improved because of these tropical feedbacks that I said earlier. Some of it might be also due to the tropical cyclones are now no longer sort of over deep, because we had a bit of an over deepening problem when we were running the atmosphere only model. And a bit like the previous talk, when you have a couple of feedbacks producing a cold wake, which we do have in the couple model, then that helps reduce the strength of those tropical cyclones. Okay, so now I'm going to talk about operational implementation. So far, all the results I've presented so far are basically results of the coupled NWP model based on an uncoupled data analysis system, or data simulation system. So this is where we run the operational data simulation cycle with our atmosphere only model, and the ocean data simulation cycle with the ocean only model separately, and then the outputs from the data simulation then feeds into the couple model forecast. But that's not what's going to go operational. What's going to go operational is the bottom diagram, where we run. We still run the sort of data simulation separately in terms of ingesting the observations, but then the couple model then produces the forecast for the next 6 hours, which feeds into the couple model background for the next data simulation cycle. And that means that the sea surface temperatures are consistent, the atmospheric and ocean fields above and below that are consistent, and so that produces a much better forecast and reduces some of those 2 meter temperature biases that I showed you earlier in the verification plots. So the plan is to make coupled NWP with weekly coupled data simulation operational from autumn 2021. The resolution will be N1280 L70, that's 10 kilometers resolution in the atmosphere or per quarter. So it's the same as I showed you from the results earlier for the deterministic model. We will also run an ensemble of coupled NWP models. For these, the atmospheric resolution will be reduced, so 20 kilometers atmospheric resolution. The ocean resolution will still be the same, or per quarter. We will run the model at a version of the science called GC4, which is a little bit on from the PS41 science I showed you earlier. Just to sort of put this into context, GC3 science is what we used in the CMIP6 mission. So this is a step on from that. And this was frozen in March. The ensemble will use ocean analysis from the weakly coupled DA, but we're only going to use sea surface temperature perturbations. So we're not going to perturb below the sea surface. So for the ensemble, I guess we're not going to get as much spread as we would like because we're only perturbing the sea surface temperatures. So a further future implementation would then be to perturb the depth of the ocean to get a proper ensemble spread within the ocean. So one of the things that most modeling centers are facing is the increase in supercomputers in the number of processors, but the processor speeds are now no longer increasing. And in fact, lots of supercomputing centers are starting to use other types of architectures, such as GPUs instead of CPUs. So one of the things that the Met Office is doing is switching. Well, we're moving away from using our old unified model, so that uses a tripolar grid in the bottom left. Sorry, uses the latitude-longitude grid in the bottom left. And we're moving to a new model we're calling ELFRIC, which has a cube sphere grid. So this allows us to run on even more processors, so it should be a lot more scalable. Now no longer has a convergence point at the north and south pole, so stopping instabilities at the poles. And we're making it so that it is the science and the technical aspects is going to be separated, so it should be able to work on all different sorts of computer architectures. We're rewriting the core to as a new gung-ho dynamical core as well. So, okay, so that's one aspect of the things we're going to improve. So that the diagram on the left is what I've already described, the current coupled NWP model that we're hoping to get operational. The diagram on the right is what we're moving towards in the future. So we're changing the UM to ELFRIC and with its cube sphere grid. And we're also going to upgrade the ocean resolution. So we were a orca quarter. We're going to move up to orca 12th of a degree in the ocean. The sea ice, we're switching out the size sea ice model for SI cube sea ice model. So this is part of the NEMO consortium. All these models output to XIOS. So XIOS is the IO server that NEMO uses, but we're going to move to the ELFRIC, and Jules and SI cube all use it. And we're also going to put in an optional wave model, WaveWatch 3, which is also going to communicate via OASIS 3 MCT. So we're going to have three-way coupling. And WaveWatch 3 has its own grid as well, so there's three grids to regrid between. Okay, so that's it from me. So just to summarize, using coupled NWP gives better verification scores than atmospheric model, except those 2 meter temperatures. But the remaining 2 meter temperature issue can be fixed by verifying both versus a weakly coupled data assimilation analysis and by using austere lake SSTs. SST forecasts are improved over persistence, except in the Southern Ocean. 500 hectopascal heights, 250 hectopascal winds, and tropical cyclones are all on average improved. We are aiming for the operational coupled NWP model to be GC4 in autumn 2021. The Met Office coupled NWP is moving to a new sea ice model, SI cube, so that's going to be called the GC5 version of the science. A high resolution ocean, so it's Orca 12, and then a cube sphere grid atmosphere, which is the ELFRIC model, which will go into the GC6 version of the science with an optional wave model, WaveWatch 3. Okay, that's all from me. Thank you very much.